Now we will show that the kernel of a linear transformation that takes vectors from a vector space V to a vector space W, we will show that the kernel of T, so this is not kernel of V or kernel of A, it's kernel of T, being all of the vectors that get sent to the zero vector in W, we will show that the kernel of T is a subspace of vector V. So for this, maybe you recall from chapter 4 that we have to first show that the kernel of T is non-empty. So we have to show that there is something in the kernel of T. So to do that, we do a little trick. So we try to figure out if there's something that'll get sent to zero. So I have a feeling that the zero vector in V will probably get sent to zero. So I am going to write the zero vector in V as the scalar zero times some vector in V. Because V is a vector space, 0 times V will have to equal the vector 0 because of this is one of the vector space axioms. So now we apply the fact that T is a linear transformation, so the constant can come out front. So now this is the scalar 0 times the image of V. Whatever the image of V is, if we multiply that by 0, we are going to get the vector 0 because this operation happens in W, which is also a vector space. So we see that the vector 0 in V gets sent to this vector 0 in W, and so this vector is in the kernel of T because it gets sent to 0. So 0 is in the kernel of the transformation. The second thing we have to show is that if we add two things that are in the kernel of T, we get something in the kernel of T. So we have to show that the kernel is closed under addition. So I'm going to say let U and V be in the kernel of T. What does that mean? Then T of U goes to 0 and T of V goes to 0, right? So that's what it means for me to pick vectors in the kernel of T. And since the kernel of T is not empty, I can pick vectors in there. So now I'm going to try and show that the sum of U plus V gets also sent to 0. So I'm going to put the sum U plus V through the transformation and see what happens. If this sum is also in the kernel of T, if U plus V is also in the kernel of T, then the kernel of T is closed under addition. Because T is a linear transformation, I can distribute the transformation and I have T of V plus T of U in this way. I'm sorry, it was U and V first. And so I already know that these guys both equal 0. So this is 0 plus 0. These are the zeros in W. Because W is a vector space, this equals 0. So here I showed that U plus V gets sent to 0. So what does that mean? This means U plus V is in the kernel of T. So the kernel of T is closed under addition. The addition defined in vector space V. Good. So now last thing left to show is that the kernel of T is closed under scalar multiplication. So we're going to apply C times U we're gonna put c times u, so we're gonna assume u is this vector that is in the kernel of t, right? So if I pick u in the kernel of t and then multiply it by c, now I'm gonna put it through the transformation. This is the same as c times t of u because t is a linear transformation. U is already in the kernel of t, so it equals 0. So this is c times 0, and that equals 0. So that means c times u is also in the kernel of t. So the kernel of t is closed under scalar multiplication. So by theorem, I think 4.15, in chapter 4, t is a kernel of t, kernel of t is a subspace of V, right? So because it is not empty and it is closed under addition and scalar multiplication, the kernel is a subspace of V. All right, so let's look at an example that brings us back to what we were doing in chapter 4. Now that it's a subspace, we can find a basis for the kernel of t. So to find basis for the vector space that is the kernel of t, we want to find all of the vectors, let's see, 1, 2, 3, 4, 5, x1, x2, x3, x4, x5, right? All of the vectors in R5 that get sent to the 0 vector. Let's see, if we multiply 4 by 5, 5 by 1, we get 4 by 1. So 1, 2, 3, 4 entries here. So we're familiar with solving the system, right? So it seems like we're trying to find a null space, if you remember from chapter 4. So it's all coming back, maybe. So what we're going to do is we're going to augment a with the 0 vector, and then we're going to put this in reduced row echelon form, and luckily I've done it already, and this is 1, 0, 2, 0, negative 1, 0, and then 0, 1, negative 1, 0, negative 2, 0, 0, 0, 0, 1, 4, 0, and then a row of zeros down here. So let's see. That means if I'm going to multiply this by x1, x2, x3, x4, x5, I'm going to get 0, 0, 0, 0. And so I'm going to solve this and parameterize it. So the vector, the solution space, or all the vectors in the solution space will be given by x1 is going to be negative 2s plus t. X2 is s plus 2t, so you can work out the algebra if you'd like. No t's there, negative 4t, and just t here. So that means we can split this into multiples of s, right? So we've done this before in chapter 4, and multiples of t. So it seems like this is a familiar computation, so I wonder if we can put it back in a familiar context. So these vectors span the kernel of t. This is the solution space, right? So all the vectors of this form the solution space of the system AX equals 0. So that makes these two vectors, these are going to be called a basis for the kernel of t. So if you recall from chapter 4, there was also, this was called the solution space of that system, and now we're going to call it the kernel of the transformation represented by this matrix, by left multiplication by the matrix, in the past